Hello, and welcome to Week 3, Lecture 1 of CO 442642 Graph Theory. Today we'll be talking about edge coloring. So what is edge coloring? Well, last week we had discussed coloring graphs by coloring their vertices. Here we'll be coloring their edges. So an edge coloring of a graph G is an assignment of colors to the edges of G, such that no two incident edges receive the same color. And remember that two edges are incident if they share a common end. And then in the same way as with vertex coloring, we can define a k-edge coloring of a graph G as just an edge coloring of that graph where you use the colors 1 up to k. And then the chromatic index of a graph G, which is also known as the edge chromatic number, and this will be denoted with chi prime of G, so it has this extra prime in there, is the minimum number k such that G has a k-edge coloring. So what is this? Well, a different way to think about it is by the notion of line graphs. Maybe you've heard of this. The line graph of a graph G, denoted L of G, is the graph where the vertices are the edges and two edges are adjacent if they're incident, i.e. they share a common end. So that's the definition of line graph, and then it's clear then that edge colorings of graphs are equivalent to vertex colorings of their line graphs, and hence that chi prime of G is equal to chi of L of G. But again, not all graphs are line graphs of other graphs, so kind of a special set of coloring only certain kinds of graphs, namely line graphs. But it becomes very interesting for the types of bounds that you're able to prove on this special class of graphs. So a natural question again here is, what are some natural upper and lower bounds on this chromatic index chi prime of G? Well, since we know about vertex coloring, we can take some of the bounds we learned there and apply them to line graphs. So what bounds on the chromatic index can we get this way? Well, there's the greedy bound, right? So what's the maximum degree of a line graph? Well, you can upper bound it in terms of the maximum degree of the original graph. Namely, it's at most 2 delta G minus 2 because an edge uv, well, you could have delta minus 1 other incident edges and v also delta minus 1, and you put these together, you get 2 delta minus 2, and hence the greedy bound for vertex coloring, which show that chi prime of G is at most 2 delta G minus 1. So that's pretty easy to get a bound that's linear in the original maximum degree. So that's very nice. And then what about lower bounds? Well, the clique number of a line graph, if you think about it, is at least delta the maximum degree of the original graph, as all edges around a vertex form a clique in the line graph. They're all incident with each other. So that's a lower bound, and hence chi prime of G is at least delta of G. So you have this kind of linear upper and lower bounds in terms of delta of G. And I'll just remark, if you think about it, actually omega of the line graph is equal to delta of G if delta is at least 3. So when you're dealing with paths and cycles, if you have triangle, the omega of the line graph could be 3, of course. But beyond that, when you're at least 3, you can't actually get a larger clique than around a vertex in this way. So those are the upper and lower bounds we kind of know from understanding vertex coloring. And then here are some questions. Can we meet this lower bound? So for which graph does chi prime of G equal delta of G? Well, maybe pause and think for a moment. So maybe you know some of this. I'm not going to do all of them, just a couple of them. So one easy one is even cycles, right? Because even cycle, the line graph of an even cycle is itself. It's the same even cycle, and those have chi 2, so they have chi prime 2. So you can two-edge color even cycles. The less obvious one is kn, where n is even. So there you can decompose it into the perfect matchings. So if vertex coloring was decomposing into dependent sets, edge coloring is decomposing into matchings, and here we can indeed cover this with the right number of matchings, namely n minus 1, the max degree of kn. Are there graphs, though? Here's another question, where chi prime of G is greater than delta of G. Can you always get this delta of G? So again, think for a moment and come up with some classes of graphs. And the answer is, well, 1, odd cycles, right? So they have delta being 2, but if you think about it, you can't, again, the line graph is itself, it's an odd cycle, and those have chi being 3, so they have chi prime being 3. What about another one? Well, complete graphs, where n is odd. It just turns out, since you can only use near perfect matchings, there just aren't enough, the colors can only use, n minus 1 over 2 edges, and so there are just too many edges that need colors. So you'd actually need to use delta plus 1, namely n colors, when kn is odd. So those are two kind of nice classes, even cycles, odd cycles, even complete graphs, odd complete graphs, that show some disparity there. And what about another large class of graphs? So it turns out, maybe you've heard this from undergrad graph theory, that if G is a bipartite graph, then chi prime of G is equal to delta of G. So it's not just even cycles, actually all bipartite graphs. So there are more, as evidenced by the even complete graphs, but at least all bipartite graphs satisfy this nice lower bound. So they meet it. And that was a theorem called Konig's theorem, but proved in 1960. So very classical. And I thought I'd go through some proofs of this. So let's do some proofs. So I think you've probably seen this first proof of Konig's theorem, so I'll just run through it for you. But I'm going to do a second proof, which is going to show off some of the techniques we'll be using in edge coloring later when we talk about Vizing's theorem. So here's the first proof of Konig's theorem. It suffices to prove the theorem when G is regular, or delta of G regular, since every bipartite graph G is a subgraph of some delta of G regular graph H. So you can kind of embed it into a larger graph, which is actually regular, with the same maximum degree. And exercise, prove this yourself. It's not very hard. You can use some forms of induction, but it's a nice little exercise. But I'll just use that fact, so it suffices to prove it for delta of G regular graphs. We can assume your delta G regular. And now I'm going to proceed by induction on the max degree. If the max degree is 0, there's nothing to show. There's no edges anywhere, so there's nothing to color. So that'll be fine. Chi would be 0. So we assume that delta is at least 1. And then I do the following. I take any subset of A, so if G is equal to AB, has two sides. I would double count the edges between S and its neighbors on the other side. And a simple counting argument shows that delta times S has to be then the number of edges because you're delta regular, and this is upper bounded by delta n of S because they have degree at most delta, and thus S is at most n of S, which is good because then I can use Hall's theorem. So by Hall's theorem there exists a perfect matching M of G, and then A and B are equal actually, and then you actually have this matching saturating A, and so perfect matching. And so by induction, G minus M, when you delete that perfect matching, that would have a delta minus 1 coloring because the maximum degree of G minus M would have gone down by 1. And then I just let phi of E be equal to delta of G for each E and M. So I add back a matching, I color it all with this last color delta, and I get a delta coloring of G as desired. So you've probably seen this proof where you just apply Halls to extract perfect matchings in bipartite graphs. So very nice. But today I wanted to do a second different proof of Konig's theorem that uses the ideas we'll need for the proof of Vizing's theorem. And it goes like this. So first let me introduce a Kempe chain. So a Kempe chain is, I'm given a partial k edge coloring of a graph G. So here I'm going to use partial, meaning not all the edges have to be colored. That'll be useful for the proof here and for Vizing's, as you'll see in a bit. But so it'll give me that. Now if I give you two colors A and B and a vertex V, then the AB chain at V and phi, and I'll denote it by PV phi, is the maximal path cycle of A and B colored edges containing V. So at any vertex, I just take kind of all the, this path or cycle you get. Really what I'm doing is I'm taking the component induced by the edges colored A or the edges colored B that contains V. And you know, if A and B are not, if there are no edges colored, those incident with V, then you just get V itself, which is path on zero, on one vertex, 0 edges there. Otherwise, if you think about it, it'll be a path of only one, a path or maybe a cycle if it ends up being a perfect AB cycle, and then be an even cycle because A and B would alternate. So these are the options. These are called Kempe chains, as developed by Kempe in his failed proof of the four-color theorem back in the late 1800s, but they're key actually to edge coloring. So we're going to use them, and an operation we'll call switching. So the coloring phi prime obtained from phi by switching, also known as recoloring, this path PV, is defined as, well, we'll let phi prime of E be AB minus phi of E, so you just switch the colors A and B on that path, if E is in the path, and let phi prime of E equal phi of E otherwise. So that's switching. It's something you can, nicely do. You can even do this in vertex coloring. These components won't be paths anymore, but you could switch the colors between A and B. But this works particularly nicely on paths because it keeps them being paths and or cycles. And then one last definition I'll need is that of missing colors. So again, I'll take a partial k-edge coloring of a graph G, phi, and here I have to specify what k is, and we'll say a color A and k is missing at V in phi if A does not appear on any edges incident with V. So kind of you're missing around that vertex V at V. So what colors are there? And it actually turns out it's less important the colors that are there than the ones that are missing, as you'll see why in a little bit. And that's important enough that I'm going to give it some notation. So now this is not exactly standard, but for some of these edge coloring proofs it is. We let phi of V denote the set of missing colors at V. So that doesn't really mean anything. It doesn't give you a coloring of the vertices. Indeed, these are sets of colors, but it's just going to be helpful to keep track. So since the edges are the ones receiving the colors, we'll just use this in a terrible abusive notation to denote the set of missing colors at V. And so that's what we have. So we have Kempe chains, we're switching the Kempe chains to get new colorings, and we'll talk about these missing colors at V and their set of missing colors. Very important. All right, given all that, and try to internalize, I really think through, I'm going to do a second proof of Konig's theorem using Kempe chain switching and missing colors, and that'll set us up, prepare us for these proofs of Vizing theorem that use the same ideas. So Konig's theorem, a second proof. Here we go. Again, we'll proceed by induction on the edges, number of edges of G. If that's empty, then there's nothing to show for edges, so we assume that E is non-empty. So that means there's at least one edge. So let E be this edge with ends U and V, and by induction, there exists a delta of G edge coloring of G minus E. So if I delete that E, then I can get a coloring. Then where do we go? Well, let phi be such a coloring, but now I'm going to be a little bit tricky. I didn't have to do it exactly like this, but it'll smooth the proof a little bit and also give you some insight into other ones like Vizing's theorem. So here I'll do it such that phi of U intersect phi of V is maximized, the size of that. And again, those are the missing colors. So that maximize the number of common missing colors at U and V, the ends of this edge E. And if you think about it, those are actually non-empty. So U and V are at least both missing a color because their degree in G minus E is at most delta minus 1, and E isn't colored. So they can see at most delta minus 1 colors, so each will have at least one missing color. And so we're using that we're using delta edge coloring right here. Then what? Well, if they have a common missing color, then you just color E with that color. So you let phi of E in the intersection of the two, and then that extends it to delta edge coloring of G as desired. So you can actually assume that they have disjoint sets of missing colors. So you see where we're using missing colors. And I'll just, again, take one from each. So let A be a missing color at U and B be a missing color at V. And then think about the path PU AB phi. So this is this AB path that starts, contains U. And actually, if you think about it, it has to start at U because U is missing A. So it's going to have degree at most 1. It could have a B-colored edge, maybe it doesn't, maybe then the path is just U, but it is a path, so it won't be a cycle, and it will start at U. U will be an end of that path. And then the question is, where is V? Is V in the path? Well, if you think about it, then if V is in the path, V is missing B, so the edge next to it has to be A. Well, the edge next to U had to be colored B, which would mean the path would have even length. That's an even number of edges. But then if you added back the edge E, you'd get an odd cycle in G. So P plus B, E would be an odd cycle in G, contradicting that G is bipartite. So here's where we're using the bipartiteness of Konig's theorem very nicely, that these kind of paths would actually, an even path would give you contradictions. So that means we can actually assume that V is not in this V of P. But then what does it mean? Well, then we can switch, right? So now U and V are in different kind of AB components of G. So we can switch P and not affect anything outside that component, at least in terms of A and B. In particular, we don't affect V. So switching P yields a new coloring, let's call it V prime, and it's clear then that this B, which was missing at V, will still be missing because I didn't affect A and B around V. But now we've switched A and B at U, and all the things on the path, the P there. So in particular, that means where A was missing in phi at U, we now get that B is missing in phi prime at U. So B is a common missing color in phi prime of both u and v. But then why did we choose phi prime instead of phi? Indeed, that's a contradiction to this choice of phi, since we're supposed to maximize the number of common missing colors. So a very nice proof, a second kind of proof of Konig's theorem, where we use the ideas about missing colors there at the end and maximizing the common ones. And if they had a common one, just extend the coloring. Otherwise, we kind of do this flipping. We used Kempe chains, flipping to help us get the coloring. We used, again, the Kempe chains and the bipartite there to argue about the length of those. So we used all those nice ideas and concepts in this different proof. So in some ways they're the same, but really they're different, right? They're distinct at heart. One using Kempe chains and missing colors and switching, and the other just applying Hall's theorem repeatedly. So why do I say all that? Because next time we're going to be talking about Vizing's theorem. So let me just introduce it to you. Vizing's theorem from 1964 says that if G is a graph, then chi prime of G is in most delta of G plus 1. Right? So we saw that chi prime is at least delta, nicely with Konig's. If your bipartite they're equal, there are other times when they're equal, and then we showed ones where it's greater. But actually, if you thought about those examples, they were always most delta plus 1. You know, and we had this trivial bound with greedy of 2 delta minus 1, but it's kind of became with this, you know, this nice question, is it always at most delta plus 1? Can you find delta plus 2? And Vizing's theorem nicely says, no, really delta plus 1 is the answer. So you're either delta or delta plus 1 for the chromatic index. So this, you know, it's crazy, right? For edge coloring, we only have 2 options, delta or delta plus 1. That's it. So this is a very beautiful classical theorem. Next lecture, I'll walk you through a proof of Vizing's theorem using these Kempe chains, switching, missing color ideas. I just wanted to say a little bit more, which is that, so you again have these 2 types, either chi prime is delta or delta plus 1, and that became so prominent that it was given names, which may be a little bit terrible because these are very generic, but we say a graph G is called class 1 if chi prime is equal to delta, and class 2 otherwise, namely if it's delta plus 1. So we learned that bipartite graphs are class 1, even complete graphs are class 1, whereas odd cycles are class 2, and odd complete graphs are class 2. And you might then wonder, okay, can I do more? Can you tell me exactly which ones are class 1, which ones are class 2? And that would be very nice. It just seems impossible, because it turns out that deciding if a graph is class 1 versus class 2 is an NP complete problem. So if there was some very nice characterization, that would probably mean there would be a polytime algorithm to decide this, and it would collapse the P versus NP hierarchy. So this is really, even though there's really 2 options, delta and delta plus 1 for chi prime, it's probably intractable to actually come up with any characterization between the 2. So Vizing's theorem is nice and satisfying in that you couldn't really hope to come up with a theorem that tells you when it's actually delta, but at least we've gotten it down to delta and delta plus 1. So that's where we'll end today. Tune in next lecture where we'll do a proof of Vizing's theorem.